Okay, so this is my beam, and I'm going to draw it like that. And this is the axis along which it's bent, like that. It's being bent like that. Ooh. You see that? Bent like that. So this is your, we decided right at the axis of symmetry. So this axis here is my axis of symmetry, which is now going to be my z-axis because that's the original of y, and this is my x-axis coming out of the beam. You see that? This is my neutral. Actually, we call it neutral axis, but it's the whole neutral surface. That is a whole sheet of fibers that sit right in the middle of the beam here, that are in the symmetry between the top and the bottom of the beam. Imagine like with a knife, you go through, zip, you expose a surface here. That whole surface is neutral. It's a neutral surface to the middle of the beam. So this is my y. Let's say that I go out at a certain y here. So this is a certain distance from the neutral axis y. Remember that the radius to get all the way here is rho, right? The radius rho is now defined as the radius at the neutral surface. That is the definition. How much is the radius of curvature at the neutral surface? That is the definition of rho. So my rho is radius of curvature at the neutral axis. And so that is my definition of the curvature. The curvature is at y equals 0. So the curvature is defined at y equals 0 at the neutral axis. What if I am a little above the neutral axis, say here? What is going to be the radius of curvature, r, at y? So the radius of curvature at y is, so if what I'm doing is I'm moving up from the neutral axis, and I'm wondering what is the radius here? It's not the radius of the top. It's not that small, right? But it's smaller than rho because I moved up a little bit. I moved up by y, exactly y. My radius here is rho minus y. As simple as that, right? Great. So now, what can I find? I can find then what is the length. Like in this beam here, you see somebody went and nice conveniently for me drew lines along the length of the beam. So now I'm looking at the length of one of these lines, not the top, not the neutral axis, but the length of a line which is at distance y from the neutral axis. Well, geometry is still the same. I still have this nice, convenient, big angle theta. So the length of this line here is going to be theta times the radius of this line. So the length at y is simply going to be equal to theta times r of y. So that's going to be equal to theta times rho minus y. This is the current length of this line here. Once it's deformed, what was the original length? Actually, let's keep a whole step. What is the strain then on this line? The strain is the strain at y. The strain, any lines which is at y, at distance y from the neutral axis, is the current length minus the original length, let's call it L0, divided by the original length. Okay? So that is going to be equal to theta times rho. What is theta times rho? That is the original length. So this thing, I can write it as theta times rho minus theta times y. Theta times rho is the length at the neutral axis, which is the original length of 0. Right? Great. So when I take L0 away from that, I get minus theta y over L0. Oh, looky, I say. I got another theta over L0. What is theta over L0? It's the curvature, 1 over rho. So out of this very simple geometry, I get an amazing result. I get that epsilon of y is equal to minus y over rho. Look at that. How neat and simple. He gets a double star. He gets a double star because this simple relationship tells me that if I want to find the strain at any distance y from the neutral axis, all what I have to do is do minus y over the radius of curvature, and that is my strain. Yes?
Y is the distance from the center to whatever?
To whatever I want to strain.
Okay.
Right? I defined y equals 0. I conveniently placed my y equals 0 at the neutral axis, right? So that y now measures the distance of any fiber from the neutral axis where I want the strain. And it has minus because for positive y's, if you go up here, this strain here is going to be negative because it's going to be compression on the top for positive curvature. Positive curvature, the beam may be smiling. These guys are squished to death. Okay, these guys are all pulled. And epsilon y is minus y over rho. Actually, I can draw it for you, what it looks like. Let's draw it. Let's draw it. If this is my cross-section, and this is the way things are curving, so that, again, this is the direction in which my moment is going. It's not a very nice arrow, but kind of. So this is my bending moment coming that way, which means this is my x-axis. Ugly. This is my y-axis. This is my z-axis. Any place which is down here at the bottom is going to have a positive strain. And actually, if the whole height of the beam is h, down here at the bottom, anything that is sitting down here, this guy, this guy, this guy, everybody is going to have a positive strain. Right? The positive strain is going to be equal to minus y, which is minus h over 2, because we are underneath. So we have minus h over 2, and we get h over 2 rho. So this is the epsilon at the bottom. We get h over 2 rho. All these guys are being pulled, and they have a positive axial strain, h over 2 rho. And then as I keep going up, here, I'm going to have less strain. Here, I'm going to have 0 strain because I'm in Switzerland. Up here, I'm going to be pushed into the beam like that. So if I draw it out, my strain is going to be positive at the bottom, negative at the top. You see? If you don't see well here in 3D, we can draw it in 2D like that. Like if I draw these lines like that, and if this is my beam coming at me, and if I draw epsilon axial as a function of y, then I have at the bottom here positive axial. Here I have net, and it's just one straight line, like that. So this is positive extension at the bottom, negative contraction at the top. You see? Actually, normally, that's the way we draw our strain diagrams, right? So if this is the beam, we just draw the y-axis and the epsilon a along the x direction so that we can see the strain. Do you see it?
And it'd be opposite if we're giving a negative, right?
Curvature.
Negative curvature.
But remember, the negative curvature would be in here, so this equation still works. Right? So the minus sign would be here. So this thing would be negative if the curvature was negative. Good question. OK. How about stresses? What do we do with stresses? OK, so if this is the strain, if I want the stress at any spot, say that I want to know what is the stress at this little area here. So this is an area which is at a certain y and a certain z. What is the stress at some position y, z? How do I find it if I know the strain? This is just axial strain. Let me put an A here to remind you that this is just the axial strain along the axis of the beam. It's the same axial strain we had in uniaxial loading. It's just that in uniaxial loading, everybody on the cross-section had the same axial strain. Now that's not the case anymore. The strain depends on where you are. If you are at the neutral axis, your strain is 0. If you're underneath, the strain is positive. If you're on top, the strain is negative. But if I know the strain, how do I calculate the stress? Do I need something new, or this is something I know already? Yeah. We know it. We use the Young's modulus. If this little section here at the Young's modulus E of y and z, whatever the material was at this spot, if I know the strain at that spot, I just multiply E of whatever that thing was times the strain minus y over rho. That is the stress at this spot here. There is nothing more to this story. We have the stress at that spot here. If homogeneous, that is 1E, same material, one material. So if the whole section is made of one single material, what is the stress profile going to look like? Is it going to look different from this? No, because it's going to be equal to this multiplied by a constant E. So this drawing here that we drew for strain, if it's homogeneous, this also is what the stress looks like. It's just that if it's strain, here is h over 2 rho. If this is the strain, if this is the stress, this is E times h over 2 rho. Right? Because it's h over 2, the y. So if I do minus h over 2 minus h over 2. So remember that here at the bottom, if the whole height is h, the y at the bottom, y bottom, is equal to minus h over 2. So if you take this one and you put it here, you find the strain at the bottom. If you want the stress at the bottom, if the material modulus is E, take the strain, multiply by E, boom, got your stress. It's not really like a major extra conceptual step to do the bending situation. You already have all your tools. You guys are so good. You guys came with me up to here. It's like you have so many tools in your bags now. You know about stress, you know about strain. With a little bit of turn of geometry, you can do beam bending. Right? Good? Excellent. OK. So we need to connect one more thing. That is, you see I put this moment M here. And I'm telling you there are these stresses here. You know, like the axial force is the sum integral over the area of the axial stresses in the A. And the torque is the, R times the area and so on. So there is a connection between, there is an equilibrium condition that connects the moments to the stresses, if these are the stresses. So how do we calculate that? And then we're done, really. I mean, it's crazy.